We're going to be looking in this chapter at what the derivative and the second derivative can be telling us about our original function and how to more accurately get a decent looking graph. So the first thing we're going to look at today is being able to find a maximum or a minimum value on a closed interval. So C is some number in between A and B on a closed interval. When you put that number in, if it's the lowest point, lowest output of everything on that function, then it's considered the minimum value. Similarly, D is on our closed interval, and if when we substitute that into our function, if it's the highest output, meaning everything is greater than or equal to our function, then it's a maximum value. So here we have a couple of graphs. We have a closed interval here starting at -1, going to +2. This would be referred to as our minimum because it's the lowest point of the whole graph. This would be our maximum of the whole graph. Yes, there's a maximum over here, but it's not the maximum of the whole graph. It's only a maximum in that local region. Now here we have an open interval. An open interval may or may not have a max or min. In this case, we do have a minimum, but because it's an open interval, it goes up to this point but does not include that point, or up to this point does not include this point. There would be no maximum. Or here we do have a closed interval where we do have our maximum again, but because it's a piecewise function, there's no minimum right here. So we also have what's referred to as a local min and a local max, where a local minimum is the lowest point in a certain neighborhood or region of your graph, but not necessarily of the whole graph. Where here, we would have a local maximum, which is just the highest point in a certain region of the graph, not necessarily the whole graph. So these extrema, the max and mins, when it's on a continuous function on a closed interval, we need to go ahead and find our critical points. And then we need to evaluate those critical points. And then we can see what we have for our max and our min based on what we get when we plug in those critical points. Now, critical points down here in red are when your derivative is either equal to 0 or your derivative does not exist. So we're going to check our critical points that happen to be on the open interval inside, and we're going to check our endpoints. Then we'll end up finding our max or our min. So here we have a cusp. Remember, at a cusp, your derivative does not exist, and in this case, it happens to be a maximum. Or here we have our derivative being 0, which you should remember the slope of your horizontal tangent line is 0, which is where a max or a min can occur. Doesn't always have to, but can occur. So here we want to find the maximum and minimum of this function on a closed interval. So the first thing you want to do is to find your derivative. So put the exponent in front and decrease it by 1. Exponent in front, decrease it by 1. Then you want to look to see where your derivative is undefined and where your derivative is equal to 0. So I'm going to start out here by simplifying this just a bit. Now, if you wanted, you could have pulled out the over 3 and pulled out the smaller of the two exponents, which would be your x to the -3. And from the top, you could have pulled out a 5. Could you have factored it? Yes. Being only two terms, once we set it equal to 0, we could just take one of the terms to the other side and solve it. But a lot of times you'd want to pull out your greatest common factor. So I took this to the other side. Now I can go ahead and cross multiply. And then we solve it for x, and we get 2. Notice 2 is part of our closed interval up here. Now, remember, our critical points are at the endpoints where your derivative is 0, which we just figured out down here, or where your derivative is undefined. Well, looking here, we have this in the bottom of our derivative. So what would cause this to be 0? Well, that would be 0. So that would be a critical point where it would be undefined. So our critical points are the endpoints where your derivative is undefined and where your derivative is equal to 0, which is 2. So these are our 4 critical points. We need to try each one of these critical points into our original function. Then we can go ahead and figure out which one is our max or our min. So we take -1, plug it into our original function up here, and evaluate it, and we end up getting 6. Take 0, plug it in. Well, 0 and 0 is 0. Take 2, plug it in. Remember, this would be a 2 squared, and you got to take the cube root. This would be a 2 to the 5th power, and then take the cube root. And then remember, you could take 2 to the 5th instead of a cube root and simplify that root. Well, if you do all that, you end up getting 3 cube root of 4, which I'd wanted an approximation, so I'd have an idea if it was more than 6 or less than 6. And then take 4 squared, take the cube root, and then 5 or 4 to the 5th, and then take your cube root, simplify it down, and in this case you would get 2 cube root of 2, which, to compare it to our normal numbers here, I wanted an approximation. So the biggest number that you get out here is your maximum. So that is 6. So your absolute max occurs at -1, and it is a value of 6. The smallest number you get out here is your minimum. So that occurs when we plug in 0, we also get out 0. That's our absolute min. For the most part, that's your process that you're going to go through to find your extrema on a closed interval. So we find a derivative, power rule here, solve it by set equal to 0 and solve it. I'm going to go ahead and divide everything by 6. This one does factor quite nicely. And in this case, we get 2, but we also get -1. But note, I'm not going to continue to work with -1 because -1 is not in my closed interval up here. So my only critical point that I get from my derivative being 0 is 2. So I'd have my 2 critical points from my endpoints of 0 and 3, and my critical point from my derivative being 0, which is 2. And all I'd have to do is plug each one of those in. Plug 2 into my original function. Notice it says f of 2, so that means plugging it into the original. Then take 0, plug it into the original, and then take 3, plug it into the original. The largest output here, which is 15, is my maximum. The smallest output of these 3, which is the -5, is my minimum. So you'll notice over here, I have the original function graph from this one up here, problem we were just working on. That is in blue. Now, if you graph this derivative right here, then we get this red parabola. Make note that when the blue function is going up, your derivative is positive and above the x-axis. So this whole red part right here is above the x-axis. So let's take a look here. Slope of this line is a fairly steep positive number, so its slope is plotted up here. Slope here is getting still positive, but not as positive. Slope here, still positive, but not as positive. Slope here is 0, so that's why we get these points along here. Also, once the blue function gets to here, our slope is 0, so your derivative is 0. Then it starts to go up again, And whenever you're going up again and you look at these slopes, your slopes are always positive, and in this case get more and more positive as you come along here. Now, in between, our original function is going down. When you look at the slope, it's negative. Look at the slope, it's negative. Look at the slope, it's negative. Negative, not as negative, but negative. So that's why it goes down, negative, 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 not as negative, but still negative. So whenever the original function is going up as you go to the right, your derivative graph is positive above the x-axis. Whenever your original graph is going down as you go to the right, the original graph is negative, meaning below the x-axis, right in here. Whenever your original graph right here is going up, your derivative is positive above the x-axis. And at the maximum and minimum, your derivative is 0. So here we have an absolute value graph. You should remember that the graph of an absolute value is in the shape of a V. So first of all, let's go ahead and write this as a piecewise function to take our derivative. So first of all, you want to look at, well, what would cause the inside of my absolute value to be 0? And in this case, you set the inside equal to 0 and you get 2. So we need to look at two parts to your piecewise. What happens when we try a number greater than or equal to 2, and what happens when we try a number less than or equal to 2? So if we try a number greater than or equal to 2, and we plug it in here, x is greater than or equal to 2 minus 2 means the whole inside is positive. If the whole inside is positive, that means your absolute value isn't doing anything. So then it would just be negative 3 minus, and then in parentheses, x minus 2. But if we tried a number smaller than 2, something smaller than 2 minus 2 would make the inside negative. Well, then the absolute value does something because it takes the opposite of that inside that's negative, and opposite of a negative you know is positive. So we'll have our negative 3, and then we got to do the opposite of that inside. So for the sake of doing our derivative, let's go ahead and distribute through, collect like terms here on the top, and we would get this. If you distribute through, collect like terms in the bottom, you would get this. So what we have here in light blue is our original function. And it's in a form in which we can go ahead and take our derivative. Take your derivative of the first one, you should know you just get negative 1. Derivative of the second one, you get 1. And notice over here, there's no equal to. Why is there no equal to when there was up here? Well, remember, at 2, that's the point of your v, which is a cusp. And according to your vocab, your derivative does not exist at a cusp. So that's why there's no equal to here on our derivative. So our critical points would be our endpoints, and where your derivative is 0. Well, if you set this right here equal to 0, it's never going to be 0, but it would be undefined at 2. So 2 is our only critical point in addition to our endpoints. Now, in this case, even without working it out, you should realize that 2 is going to be your maximum. Because you should know with the negative in front of your absolute value, it's going to be a V opening down. And so at that point, it would be a max. But you could actually go ahead and plug in 2 to your function, and you would get out 3. Then you could plug in your 2 endpoints, which would be when you plug in 4 and when you plug in negative 5. Plug 4 into your original function, you get 1. Plug in 5, and you would get negative 4. So of your 3 outputs of a 3, a 1, and a negative 4, you can see that your maximum is 3 occurring when x is 2. Your minimum is the smallest output, which is negative 4, and that occurs when you plug in negative 5. One last problem. So here we'd want to go ahead and do our derivative. You should remember your derivative of sine is cosine. So now we need to go ahead and do the derivative of this. Derivative of cosine is negative sine, hence that's why it switches this, because you'd be subtracting a negative. So it'd be negative sine of 2x, but then you have to do the chain rule, multiplied by the derivative of the inside, so it'd be an extra 2 hanging around. So all we have to do is set this equal to 0 and solve it. If you wanted, you could get rid of this 2 in front by factoring it out or dividing both sides by 2. But notice that this is your double angle sine formula from pre-calc. So we can go ahead and replace sine 2 theta with 2 sine cosine. But there's a 4 in front because when you use that formula, you get a 2, but you also add another 2 in front, and 2 times 2 is 4. Now we could factor, we could pull out a 2, and we could pull out a cosine. And then you're left with a 1 and a 2 sine. So 2 is never going to be equal to 0, but cosine could be equal to 0. And then you got to think, on your unit circle, where is cosine equal to 0? Well, that's top of the unit circle and bottom of the unit circle. And notice we're only going on one revolution around, 0 to 2 pi. Then you got to set the second parenthesis equal to 0. So you'd have to go ahead and subtract 1, divide by 2. And then you got to ask yourself, where is sine equal to negative 1/2 on your unit circle? Well, that's at 7 pi over 6 and 11 pi over 6. So you have 2 critical points in red, 2 critical points in blue, plus your 2 endpoints. If you would list them all in order, they would be in this order here. So all we'd have to do now is go ahead and try each one of these critical points into your original function. If you plugged in 0 into the original, you would get this. Plugged in pi over 2, you would get this. Plugged in pi over, or 7 pi over 6, you would get this. Plug in 3 pi over 2, you would get this. Plug in 11 pi over 6, you would get this. And plug in 2 pi, you would get negative 1. So look at your outputs. Whichever one is the biggest, which is 3, you would know is your max. Now look at your outputs. Whichever one or ones is the smallest is your minimum. Here we have 2 minimum because we have 2 spots. We're at that minimum value.